Hey everybody. Uh, all right. So we were talking last time about main sequence stars, like the sun, right? Um, and what defines a main sequence star? A main sequence star is a star that is powering itself by fusing hydrogen into helium in its core. That fusion reaction, that hydrogen fusion, it creates energy, it creates heat, and that's the heat that works its way out from the core out toward the surface of the star, keeping the star hot, maintaining its luminosity for as long as there's hydrogen fuel to burn. Once a star runs out of hydrogen, then it starts to evolve off the main sequence and become other kinds of stars. How does that work? What's going on there? That is what we're going to be talking about over the next two lectures. Because how a star evolves as it runs out of fuel and starts to die depends on the mass. High mass stars and low mass stars take different evolutionary paths, and they end their lives in different ways. So that's what we're going to start talking about here today. Remember that the structure of a star is based on a balance of two forces, right? What's the force that is holding the star together? Gravity. What's the star that balances out gravity and pushes outward? Pressure, right? Gravity pulls the star inward. Gravity is what compresses the interior of the star until what happens to a gas when you compress it? It heats up, right? Once the core has been compressed enough that it gets hotter than 10 million Kelvin, that's the magic number, right? The magic temperature to start hydrogen fusion is 10 million Kelvin. Once the core temperature gets over 10 million Kelvin, the nuclear fusion, the hydrogen fusion starts. That creates some new heat, and that heat creates the pressure, because a hot gas wants to expand, right? And that hot expansion pressure balances out gravity, and as long as those two forces stay in balance, you've got a nice, stable main sequence star for as long as there's fuel in the core to burn. This also explains why the mass of a main sequence star is its destiny. I know I was banging on about that a lot a couple weeks ago, but this is why, right? Because if a star is low mass, it doesn't have a very strong gravitational pull, which means gravity doesn't compress the core that much. The temperature here is, at the low end of the main sequence, the temperature is just above 10 million Kelvin. It's just hot enough to start hydrogen fusion. The hydrogen fusion isn't happening that fast. The hydrogen fusion doesn't have to happen that fast because the star doesn't need to stay that hot, which is why the star isn't that hot. Because gravity is weak, it doesn't have to be that hot, and it doesn't have to burn the fuel that fast. It doesn't have to maintain a very high luminosity, because it doesn't have to generate that much pressure to balance out gravity. And that's why these low mass stars are cooler, smaller, and lower luminosity. This is also why they live the longest lifetimes, because the rate at which they're burning their fuel is low. They can make that fuel last for hundreds of billions, maybe a trillion years. At the high end of the main sequence, these stars are really high mass. They have a very strong gravitational pull, and that means the gravity is so strong that the core gets compressed to very high temperatures. It's burning that fuel really fast. It has to be hot. It has to burn its fuel fast in order to make enough pressure to balance out the insanely strong gravity. And that's why the high mass main sequence stars are the hottest, the brightest, the largest, and the shortest lived. Because the only way to keep pressure in check is to burn that fuel so fast. And that means you run out of fuel in less time. So that's why the mass of a star is its destiny. Because all the other properties of a star, the radius, the temperature, the color, the luminosity, all of those properties of the star are in service to the fact that this star can't live unless pressure balances gravity. Gravity is this constant threat. Gravity is the barbarian at the gates that is always threatening to cause the star to collapse, implode on itself, if there isn't enough pressure. And therefore, these stars have to keep up the pressure in order to balance gravity. Now, I said a minute ago that stars, low mass and high mass stars evolved differently. So, what do I mean by high and low? Well, stars of about 1.5 or 2 solar masses or below, those are quote unquote low mass stars. So, our sun is a low mass star. Stars that are over 2 solar masses, you could say that stars of above 2 solar masses are high mass stars. But there's kind of an intermediate ground there. So you could say that stars that are 2 solar masses and up, those are quote unquote high mass. But for reasons we'll get into in a minute, the stars that are between 2 and 8 solar masses are, you could call them intermediate mass. They're middle mass stars. And then stars that are over 8 solar masses, those are the O and B type stars that are definitely high mass. All right. So we're going to start in this lecture. We're going to start talking about low mass and intermediate mass stars, and then we'll get to high mass stars in the next lecture because again, it's a very different story. So, okay, first thing, low mass stars like our sun. There's a lot going on in this graph, so let's explain here, right? When a star is born, what is it made of? Well, it's mostly hydrogen and also a lot of helium and a little bit of metals, a little bit of heavier elements like carbon, oxygen, but not so much as to really matter on this graph. So the vertical axis here is the percentage, and the horizontal axis is the radius. So the center of the star is over here, and the surface is over here. And so when a star is born, it's just made of 75% hydrogen, 25% helium throughout the whole star. But then as the star comes alive and becomes a main sequence star, hydrogen turns into helium. And therefore, in the core, and only in the core, is the star hot enough for hydrogen to convert into helium so that as the star lives its main sequence lifetime, helium is building up and hydrogen is being depleted in the core. The rest of the star doesn't really know what's going on. The rest of the star, the outer layers of the star, are still 75-25, hydrogen to helium. And so as these stars, from birth through middle age, like the sun is today, to the beginnings of its death, that just the reactions in the core are running out of hydrogen and building up helium. Until finally, at the very core of that star, it's 100% helium, no hydrogen, and if there's no hydrogen, then there's no hydrogen for nuclear reactions. If there's no nuclear reactions, then that star can't generate any new heat. If there's no new heat, then pressure starts to lose. And pressure has to win, or else gravity wins. Sorry, pressure has to balance gravity. Pressure doesn't win, but the pressure has to balance gravity. So everything is fine. As far as the star is concerned, everything is fine as long as there's hydrogen fusion happening. But once the core has converted to completely helium, all the nuclear reactions stop. Pressure starts to lose, and gravity starts to win. And that's when things start changing much more rapidly. Right? This, on the outside, if you're here on Earth looking at a star, watch this happen, then what happens is you've got a yellow main sequence star like the sun, and that star starts to puff out. It starts to expand, and so it's getting larger, and the surface cools off. And so this is where a main sequence star evolves and becomes a red giant. So this is what the sun is going to do in a few billion years when the sun runs out of hydrogen fuel. Why, though? Why does a star... I just said a minute ago, gravity is winning. If gravity is winning, why is the star expanding? And the answer is because of what's happening in the core. All right? While the star is a main sequence star, you got this hydrogen burning core, and then you've got all the hydrogen in the outer layers of the star that are not undergoing nuclear reactions.
as soon as the core has become completely helium, pressure loses because there's no new nuclear reactions, and gravity starts to win. And when gravity starts to win, the core starts collapsing. The core starts to contract. And if the core starts to contract, then what happens to a gas when you collapse it, compress it? It heats up. If that helium heats up, then pretty soon all the heat coming off of that helium core is going to heat up the hydrogen right on top of it. There's this little shell of hydrogen gas right on top of the helium core, and as this helium core contracts, that helium is radiating heat, and it's going to heat up that layer of hydrogen right on top of it until that hydrogen gets above 10 million Kelvin. Once that hydrogen gets above 10 million Kelvin, a new round of hydrogen fusion is going to start. There's now a little layer of helium. There's a little layer of hydrogen on top of the core, simmering, burning hydrogen, all in creating new energy, new heat. And so now, what happens? All the outer layers of the star here, the outer layers are being heated up from underneath. The outer layers of the star are being heated up by the heat coming off the helium core and the heat coming off of this hydrogen burning layer. All of that heat is being radiated out into the rest of the star. And what happens to a gas when you heat it up? It expands. And so the outer layers of the star are being heated up from underneath. Those outer layers puff out, expand, and then what happens to a gas when you let it expand? It cools off. So that the inside of the star, the core of the star, is heating up because the helium core is contracting. But the outer layers of the star are taking that heat, expanding, and cooling off. And that's why the star is getting bigger, and it's cooling, and the outer layers of the photosphere are cooling off, and so it's turning red. That's why it's called a red giant. The core of the star is heating up, but the surface, the photosphere, is cooling off. All right? So that keeps on happening. As the helium core gets smaller and smaller and hotter, that star slowly creeps its way to getting bigger and cooler and bigger and cooler and further up the red giant branch. At the same time this is happening, there's all this extra helium ash that is being generated by the hydrogen burning layer. And that helium ash settles down. It settles down onto the helium core, which adds mass to the helium core. If the helium core is getting more massive, gravity is getting stronger. If gravity is stronger, then the helium core is going to contract down even more. And that's going to heat up the core even more. And that extra heat is going to drive even more hydrogen burning in that little layer on top of it, which is going to create more helium ash. And that helium ash is going to add weight to the core, which causes it to contract even more, heat up even more, drive more hydrogen burning in the hydrogen burning layer, which creates more ash, and so on and so on and so on. We've got a vicious cycle where as that helium core gets heavier and heavier, smaller and smaller, there's even more heat being dumped into the layers on top of it, causing the star to expand and puff out and turn into a red giant. And this just keeps on going, more and more and more and more. And the helium in the core is getting smaller and smaller, denser and denser, hotter and hotter and hotter and hotter, until finally the helium core, gets hot enough for the helium to start fusing. The magic number here is 100 million Kelvin. This star will creep its way up the red giant branch, and that helium core is getting hotter and hotter and hotter and hotter and hotter until finally that helium core has contracted down and it hits 100 million Kelvin, and then, like throwing lighter fluid on a campfire, whoosh, all of that helium ignites. And it now the helium is fusing with more helium to generate new heat. There's now new nuclear reaction happening in the core. It's not the fusion of hydrogen, it's the fusion of helium. And that's going to create a second round of nuclear fusion. This is the brief second life of this star. The star is now able to generate new heat, and that's going to, once that heat works its way out to the surface of the star, that star is going to become yellow again, or maybe sometimes whitish again, and the star becomes what's called a horizontal branch star. A horizontal branch star is sort of like a yellow giant, right? It's yellow hot again. It's the same temperature as the sun, but it's about 10 times bigger than the sun is, and so it's higher luminosity. These horizontal branch stars are being powered by, the heat, this extra luminosity is being powered by two kinds of nuclear reaction. The helium fusing into carbon in the core, and the hydrogen fusing into helium in that shell right on top of the core. And so that's what these horizontal branch stars look like. They are, you got the helium fusing into carbon in the core, you've got the hydrogen fusing into helium in that shell right on top of it. The heat from the helium fusion and the heat from the hydrogen fusion is all being radiated out into the outer layers of the star until they reach the surface, and so the surface glows yellow hot with about 100 solar luminosities. So it's the same color as the sun, but it's 10 times bigger, and therefore it's 100 times higher luminosity. Why does it take this dramatic phase change, right? Why does it take this long? Why do we have to go through that vicious cycle of and the answer is because remember how hydrogen fusion happens. Hydrogen fusion happens when the hydrogen atom and the other hydrogen atom collide fast enough that they can fuse, that the strong force can fuse them together before the electric force has a chance to push them apart. The magic number there, the magic temperature where the hydrogen collides and sticks is 10 million Kelvin. Well, with helium fusion happens according to what's called the triple alpha process. The triple alpha process basically means it takes 3 helium atoms. 1, 2, 3. The first step is that you take 2 helium atoms, they collide, they turn into beryllium-8. Beryllium-8 is a pretty flimsy atom. It's a pretty fragile atom. So if the beryllium-8 just kind of hangs out for too long, it'll eventually break down. Either it'll break down into your 2 heliums again, or it'll break down into something else that's even less useful. So you need to fuse the 2 helium into the beryllium, and then that beryllium needs to get fused onto a third helium to become carbon-12, and carbon-12 is nice and strong and stable, so that you create a stable end product. These 3 heliums all have more electric charge, which means the electric repulsion is stronger, and that means these atoms need to be going even faster. They need to be even hotter. They need to be colliding much hotter, much faster, so that they can glue together by the strong force and not push each other away by the electric force. That's why it takes until 100 million Kelvin. When you've got more protons in play, when you've got more positive charges repelling each other, those atoms need to be hotter in order to get them to fuse. Otherwise, they just bounce off each other. All right, so this helium burning phase, this horizontal branch, doesn't last that long. Why doesn't it last that long? Well, one reason is because it's burning its fuel 100 times faster to maintain 100 solar luminosities. So the star climbs up the red giant branch until the helium reaches 100 million Kelvin, and then the helium ignites, and it's going to sit here. Oops, pardon me. That star is going to sit there on the horizontal branch as long as there's helium to burn, but that's not going to be that long. Eventually, that horizontal branch star runs out of helium. And when that helium fuses into carbon. And so once that horizontal branch star has completely converted its core into carbon, that vicious cycle starts up again. The carbon core now starts to contract and heat up. And then that carbon core heats up the helium right on top of it until the helium reaches over 100 million Kelvin. And then the helium starts to fuse and burn into carbon, which also releases some heat. And that heat, the heat coming off the carbon core and the helium burning shell, heats up the hydrogen right on top of it until the hydrogen is pushed over 10 million Kelvin, and then the hydrogen starts to burn into helium. So this is usually what's called double shell burning, where you've got this contracting carbon core. Gravity's winning. Gravity is pulling the carbon in, which heats up the hydrogen to start fusing, which heats up the helium to start fusing, which heats up the hydrogen to start fusing. And all of this heat, the heat from the carbon core and the heat from the helium fusion and the heat from the hydrogen fusion, all of that heat is being very rapidly dumped into the outer layers of the star. And those outer layers get heated up, they expand, those outer layers expand and cool off and turn back into a red giant. So this star expands back up the red giant branch. It turns into a red giant again. And then it just keeps on expanding. There is so much heat from the carbon and the helium and the hydrogen. There is so much heat being dumped out of the core of the star that the gas in the outer layers expand, and they just keep on expanding. This is the very last stage of the life of a star like the sun, right? The sun has lived at this point for about 10 billion years. 90% of that lifetime has been as just sitting there on the main sequence, a nice stable main sequence star just like the sun is today. That last 10%, the last about a billion years of the sun's life, is spent with it climbing up the red giant branch, then becoming a horizontal branch star, climbing back up the red giant branch, and as it's doing that, as it climbs up the red giant branch, it's a higher luminosity. How does it get to be a higher luminosity? It must be burning its fuel that much faster. And if it's burning the fuel faster, it's going to run out of fuel. The helium burning phase happens much faster because it has to. It has to burn the helium faster to maintain these high luminosities, to keep gravity at bay. At the very end, you've got this carbon core giving off so much heat all at once that the gas in the outer layers of the star, they get heated up from the core, the gas expands, and it just keeps on expanding until the gas blows away completely. In the outer layers of the star, pressure wins, gravity loses. And there's so much pressure has built up inside the star all at once that the pressure just pushes the gas outward and it just keeps on going. What gets created is what's called a planetary nebula. That's what you're looking at right here. This is the ring nebula. This is a different kind of nebula. We haven't really looked at one of these before, but a planetary nebula is what you get when a low-mass star like the sun dies. The outer layers of the star have been blown away, and they're just going to keep on blowing away. The ring nebula is not that old, and so give it another million years, and all of this gas will just have blown away entirely. In the core, though, that carbon core has lost. Gravity wins, pressure loses, and gravity takes that ball of carbon and crunches it down one last time and contracts that carbon core to become what's called a white dwarf. This is what a white dwarf star is. A white dwarf star is small because it's just the core of the star. That core has been imploded down. I shouldn't say imploded, it's not quite an implosion, but the carbon core has been contracted down by gravity to become even smaller, even denser, and even hotter. White hot. That's why a white dwarf star is so hot, but also so faint. White dwarfs are low luminosity because they're so small. Because that's what a white dwarf star is. It's the carbon core of a low mass star that lost the game and gravity won. One of the cool things about planetary nebula, I should say that uh, this is a little bit of a misnomer. The reason why these are called planetary nebula is it has nothing to do with planets, actually. The reason why they're called planetary nebula is because when these nebula were first discovered, a lot of these nebula look bluish green. You can get the bluish green light in here, or these ones just look bluish green. So that when these nebula were first discovered, they look a lot like Uranus and Neptune, right? They're spherical, they're round, they're bluish. They looked like Uranus and Neptune, and so when these nebula were first discovered, people thought they were discovering new planets. Um, and then it turns out, oh no, it's not a planet, it's a nebula, and therefore they called them planetary nebulas. It's a weird historical side note. These nebula have nothing to do with planets. I'm sorry for the confusion. Uh, but one of the cool things about these nebula is they're all a little bit different, right? They don't all look like the Ring Nebula. Some of them are round and spherical, and the layers of gas are all expanding. Some of them are wildly asymmetrical, which means the story that I've just told you about how the heat coming off the white dwarf causes these layers to expand. There's clearly something else going on. Clearly, with some of these nebula are nice and symmetrical, and it seems like a nice, calm expansion. Clearly, with some of these, there's some more details going on here that people are still working on. People are still trying to figure out exactly what happened, exactly what factors cause these stars to expand and puff out as the planetary nebula in such interesting ways. So, uh, that's still a bit of an open question that people are working on. But they all have the same thing in common. These are low mass stars that the core collapsed down to become a white dwarf, and all of these planetary nebula have a white dwarf at the center. Right? There, there, all of them. The outer layers expanded away, and they've just kept on expanding. Notice I said expand, not explode. The formation of a planetary nebula is not an explosion. It's not like the star boom. It's an expansion. The gas just got heated up, it expanded, and is still expanding today. If you give this enough time, if you give this 100,000, a million years, all of the gas will just expand away. It'll get blown, all the gas will get blown away, and all you'll be left with is the white dwarf. So that's the ultimate endpoint for our sun. A low mass star like our sun will be a main sequence star until it runs out of hydrogen. After it runs out of hydrogen, it'll expand up the red giant branch. It'll become a horizontal branch star briefly. It'll expand back up the red giant branch until it blows out a planetary nebula. And once the planetary nebula blows away, the white dwarf core is all that'll be left of the sun. What is the white dwarf made of? It's made of mostly carbon, because that's all the core was made of when the core contracted and the outer layers blew away as the planetary nebula. That's the story for low mass stars. I said at the beginning that there are some stars that are sort of in the middle. They're intermediate mass stars. And stars that are between 2 and 8 solar masses will live a similar story, right? The intermediate mass stars do the same thing. They expand up the red giant branch, they form a horizontal branch star. These intermediate mass stars will still die as white dwarfs, with one slight difference. They will form white dwarfs made of even heavier elements. Right? A star like the sun will never get hot enough to take the carbon and fuse it into something even bigger. In order for carbon to fuse into heavier elements, the temperature needs to be above 1 billion Kelvin. And the core of our sun will never be that hot. But the intermediate mass stars can be. So with some intermediate mass stars, you'll find that they are made of that their temperatures did get above 1 billion Kelvin, and therefore they were able to take the carbon and fuse it into oxygen or neon or sodium or magnesium, things like that. So you can do a little bit of archaeology this way. If you look at a white dwarf, and if you look at that white dwarf and it's only made of carbon, you're like, ah, that's a low mass star. That's something like our sun. If you look at a low mass, or if you look at a white dwarf star, and if it's made of a mixture of neon and oxygen, you're like, oh, that's an intermediate mass star. That star might have had a mass of like 2, 3, 5 solar masses. If you discover a white dwarf star, and there are a few, that are made of things like magnesium and oxygen, you go, oh wow, okay, that was a higher mass star. That star was able to take the carbon and fuse it to things like magnesium before it finally collapsed and turned into a white dwarf. So that star must have been, 7, 8, 10 solar masses. That star is long dead. All you're seeing is the white dwarf that's left over, right? That star could be long dead billions of years ago, but those white dwarfs will last for a very long time. So you can look at these white dwarf stars and do the work backwards to say, well, how massive must this star have been to create the elements that it could create before finally gravity won and the core collapsed down into the white dwarf. All right. So that takes us through the low and the intermediate mass stars.